Hello, everybody. So this is going to be our first lecture for today, and a large part of this course is going to be the concepts around what is it that requires us to change the way that we do things, and how does configuration management fit into this whole changes and requirements. And so my thesis in this lecture is that the changing workloads that companies have experienced as they migrate their applications to the internet requires that architectures change in response to those workloads. So, when we think about the most important topics in computing operations for your generation, I think that it's not gonna be how to do things with computers, but it's gonna be more about how to do things with computing at scale. So, how do we get things done that make sense at the scale that we need to see them happening at? If you have an e-commerce application that's making money on just advertising, well, having 1,000 subscribers is not going to get you anywhere. You need hundreds of thousands and millions of subscribers to be able to pay the salaries of the people that work on your team. And so that, go doing the e-commerce application, making it happen, that's pretty straightforward. But making it happen at the scale that you need to have it happen at to make a living, that's the hard part. And that's the challenge for your generation. So how are you going to get this done? Well, we're going to be talking about this whole issue. It's really what the whole course is all about. But the topics we're going to talk about are things like DevOps and how that applies to this computing at scale issue. Configuration as code. Of course, that's what the course is really all about. The changes in systems architectures that companies have had to embrace to make this all happen. And then information assurance. And what is that? And how does that compare to information security? Hint, it's different and much more encompassing. And how do we get this all done? So that's the thrust of the course. So what are the changing workloads that I'm talking about? Well, this is a graph that's from Facebook, and it explains it all. We don't have labels on the axes, but it doesn't matter. What I'm trying to show with this is that over this, it was something like a 8 or 10 year period, the number of users of Facebook went from like 1 billion to like 4 billion. Huge increase, huge percentage, huge raw increase. But the traffic from machine to user, that from the server, the data center, the Facebook data center, out to the user and back, that barely budged. Why? Even with 4 million, 3 million extra users, 3 billion extra users, because they got better at their application. They were able to make the traffic between the machine, the data center, and the user less per interaction. That's good. But the kind of traffic that increased to support this was the machine to machine within data center traffic. That traffic rose exponentially. Now, what does that mean? That means that Facebook changed their architecture. So Facebook is just a MySQL database application. But what Facebook did was they refactored that monolithic application into a microservice application. Now, that made the amount of traffic from the data center to the user stay very stable in the face of increasing number of users. But what it did was it made the traffic within the Facebook data centers rise dramatically, because when you go from a monolithic one machine big application to a microservice architecture where you have the big applications made up of lots of smaller applications that exist on lots of separate machines within the data center, then you get a lot of traffic within the data center between machines to provide the information that the user needs, that needs to go out to the user. And that's what we're looking at in this drawing. And it's this drawing that required the change in architectures, because this changes the workload that Facebook experiences. And in response to that change in workload, Facebook had to change their architecture. And they merge together. We have got changing in architecture, and that has an impact on workload, and the change in workload, so there's a lot going on here. But the fact remains that Facebook is quite an application and services a huge number of users, and has a huge footprint. They've got multiple data centers all over the world that are huge by any standards, and yet the square footage per user is probably pretty reasonable. So this is what we need to deal with. How do we create architectures that can handle the changes in workloads that companies experience when they go to the internet, and when they start adding new features and new components to applications on the internet? Just to give you an example of the impact of this, let's walk through this example. I love this example. It's such a great example. So if you wanted to make money on the internet with an application where you're relying on advertising to generate the money for you, then you need a lot of users. And a common number when venture capitalists decide whether they want to fund a new enterprise is, do you think this new application could get to 100 million users? And if so, then maybe it's worth investing the money in. If not, we should probably just cut it loose and let it go. But if you wanted to get to 100 million users, what kind of storage environment do you need to support those 100 million users? Well, let's work this through, just like an engineer would on the back of a napkin at a restaurant or a bar. So they would say, well, how many times is the user going to access the application? Well, if you think about a popular application that you rely on, you can come up with a number, but it's just bare bones, 10 times a day. Does that sound reasonable for a popular new application that you think is really cool? Well, if 10 times a day, which isn't many, I think about the number of times I check my email, it's certainly way more than 10 times a day. But if you did that, that means that your 100 million users are accessing the application 1 billion times per day. Well, if each user access causes 10 requests, so you've got any sort of application is going to have HTML pages, it's going to have images, it's going to have dynamic requests, it's going to have queries that flow throughout the architecture. There's a lot of things going on there. But 10 requests, if this is CNN, and when you access the CNN web page, you kick off hundreds of requests. When you access the RIT web page, you're kicking off, probably 30 or 40 requests at least. So 10 requests for each user access sounds pretty reasonable to me. But that means that you're at 10 billion requests a day that you need to satisfy. Well, if you're doing 10 billion requests a day, that means on average about 100,000 queries per second is what you're running. But that's not really a fair way to think about it, because that's assuming that your workload is very consistent throughout the day. And as we know, that's not the way the internet works. We have users that access applications at different times throughout the day all around the globe. Well, if this is an application people access during the day, well, daytime is 24 hours a day when you're supporting a global application. If it's one that people use at night, same thing. Nighttime is 24 hours a day if it's a global application. It's hard to figure that out. And so what can you do in response to that? In the response to the fact that you're not really sure how many queries a second you're going to have, but you know that it's going to be a lot. Well, if your average is 100,000 queries a second, does it make sense to double that and say, let's build an architecture that supports 200,000 queries a second? I would say that's kind of low because, we may have spikes in regions. If you look at an application like WhatsApp, WhatsApp is used globally except in the US. We're just not big WhatsAppers. Some people do, but, not that many. However, so you could say that, during the time of day when the sun is over the U.S. or whenever it is that people use WhatsApp the most, then you're going to have a dip in traffic during that time over the U.S. But that's not really true because uh, the people in Latin America are big WhatsAppers, and Latin America and South America are in the same time zones as the U.S. The time zones go from North Pole to South Pole. So just because Colombia is way south of us doesn't mean that they're that far away from us in terms of time zones. As a matter of fact, I think Colombia is like an hour or two off from us in our Eastern time zone. I was there for doing some teaching one time, and it was great. Usually I fly east to west to Dubai or something like that, and I get these incredible jet lags. But when I went to Colombia, it was awesome because it was pretty much the same time zone. So anyhow, so in, you're not going to have that dip in traffic in WhatsApp just because the sun is over the US, because the sun is also over Latin America and South America at the same time. But you're still up against this question, what numbers should I use when I build my architecture? And if you're talking about, standard load of 100,000 queries a second, building an architecture that supports 200,000 queries a second is probably not a bad idea if the penalty of your application responding slowly is significant against the users that we want to entice to use our application. Well, there's the thing. So users are not patient these days. Most users will only wait for about 3 seconds before they expect an application to respond. There's just no time. So, if you're going to have a minimum 100,000 queries a second, 200,000 queries a second is probably low, but let's go with 200,000 queries a second. So that means that, if along with the 200,000 queries a second, each query requires 10 disk seeks. All right, so you got your spinning platters. I know SSDs, easier to talk about spinning platters. So you got your spinning platters, and there's a little arm that goes back and forth on those spinning platters, and it needs to go from spot to spot based on where the files are. And the problem is that the slowest component in any computing system are the hard drives, and the slowest part of the slowest component is those disk seeks. So when that little wand is sliding back and forth across the disk, that can be really slow. Now, as we all know, when you get a brand new laptop, it seems so fast and it's awesome. But then once you've had it for a while, it seems like it slows down. What's going on there? Well, it's probably that your disk is getting full. And so as your disk gets full, then when you go to copy a new file onto that disk, it can't go in the same, can't be just one big set of data blocks on that disk. It's going to get spread out all over the place. And as your disk gets more and more fragmented with regular use, it gets slower and slower. So let's go back. So 200,000 queries a second, 10 disk seeks. That sounds pretty reasonable considering we've got 10 requests. So, that's all straightforward. There we go. So the question then becomes, what kind of a storage architecture do we need to support this? Well, if each disk does about 100 disk seeks per second, which is, pretty reasonable. They get faster all the time, but usually, all you can do to speed up a disk is to make it spin faster. So, there's physical limits and stuff, but 100 disk seeks per second is not too bad. That means that 20 million seeks per second means, which is what we came up with, means that we need 20,000 disks. 20,000 disks to support this. So we went from, just wanting 100 million users, we need 20,000 disks to support that. Well, we could try cramming 20,000 disks into one server. It wouldn't work because anytime you've got disks, that's only part of the storage requirement. There's always computing that needs to be done, that needs to exist in front of those disks to make those disks do their job well. And that computing in front of those disks is important. And so we usually do is we'll do something like 2 to maybe 4 disks per server. But let's say we did 2 disks per server because each server's got that computing that needs to be in front of the disks to make everything come together. So if we did 2 disks per server and we need 20,000 disks, that means we need 10,000 servers. 10,000 servers. Now, is this for the compute side of this application? No, this is only the storage side. On top of our 10,000 storage servers, we would also need more compute servers. And there's going to be database servers, there's going to be application servers, there's going to be web servers, lots going on. This is just for the storage component here. Well, if you have 40 servers per rack, which, those are the pizza box servers, standard rack size, you get 40 servers per rack. And that means that we would need about 250 racks, which if you need 250 racks, that means you need about 150 meters of rack space, which is probably more than we could fit into SysLab. So, this is a huge amount of space. Now, along with the space, you need people to support this. And, so, first we're going to have people who do rack and stack for us. So we're going to get all these new servers in. We're going to screw them into our racks. We're going to configure them, with the disks and everything. We're going to plug them in. We're going to, test them out, make sure that they work and everything. And then we're going to do that for all 10,000 servers. And then those rack and stack people are mostly going to go away. Now, who are those rack and stack people? They are technicians, good people, hard workers and everything, but they are technicians. They do their technical job and then they go away. Along with those technicians, after they're kind of gone, we've got to have, well, before they get there, we have to have designers that can design this large storage environment. And then after the technicians leave, we have to have the systems people who maintain this stuff. and keep track of this storage environment, because with 20,000 disks, we're going to have individual disks that fail every day, probably multiple disks that fail every day. We're going to have lots of questions about how to optimize this pretty large storage array, and there's going to be a lot to go on. So, if each one of these servers costs $3,000 or $4,000 a piece, which is pretty reasonable for enterprise scale servers, then at $4,000 a piece times 20,000 times 10,000 servers, then we've got $300,000 worth of servers. That's all right, or is it 3 million? I think it's 300,000. And they're going to fail periodically. So we're going to have extras around, and and then we've got to have people who maintain this thing that make, 100 and something $1,000 a year plus fringe benefits. And in the U.S., we usually count our fringe benefits, health insurance and life insurance and all that kind of stuff. That's usually about 30% of the salary of a worker. So if you pay them $100,000, you should figure about $30,000 per year in benefits. So your $100,000 salary for that person costs you $130,000 times, how many workers? Is it one? No way. That worker's got to go on vacation. They, are going to be walking around on the street. Well, look, with those big, buses coming by ready to run them over at any second. So, we've got to have at least, is it two? Is it three? Do we need people here every moment of every day? Probably not, but certainly on call and available. There's probably going to be somebody be there every day. So let's say three at $130,000 per person. So that's about $400,000 in salaries per year, and that continues every year. We got, I think it's 3 million now that I think about it. $3 million worth of computers. This is big, expensive. And this is just the storage side to support getting to a number of users that makes it worthwhile to run this application on the internet. It's an amazing thing. But this is where we're going with these web scale applications. And I want you to know about the scale of these things and what it takes to build an architecture to support them. That's my main goal for